About exam 4. That is coming up next Tuesday. I think you want it to. I think you like. I would cancel it, but I just feel so bad about you guys getting all those zeros. So let's do it. I want you to have those points. Oh, I see what you mean. Yeah, that's true. No, I'm not doing that though. That would just be worse. It would be hanging over your head. You still wouldn't study. You just feel bad about it. You know what I mean? Let's just get it done. I know. I know how it goes better than most, better than you. I've been through a lot more Thanksgiving breaks with stuff hanging over my head that I didn't do than you have. So exam 4 is Tuesday. That is the 20th. Yep. And the topics are going to be everything up through Newton's laws. Yeah, but there are 3. In the class. We don't really talk about the first one. We just talk about the second and third. You could do everything with only the second, but I'm going to talk about the third one today. The first one we only talk about in lab. We might be out of labs. I'll have to think about that, but we would talk about the first law if we had more labs. Uh, I don't know. I think we might be, because we have one more lab exam, and then the last lab after the exam is the post-test of the intuition test. It doesn't affect the grade, no. But I'll give an incentive to make sure you come. I'll give a point incentive. Yeah, that's correct. Well, it sort of, you could use it on the test, but you could get by fine without it too. It's mostly like a conceptual thing, but okay. So uh, Newton's third law, and to introduce this, so Newton's third law corresponds to the third common misconception. Remember the first two? They keep being on quizzes, so you should remember all these. The first one is that people often think that gravity makes heavier things fall faster, when really, if there was no air resistance, all things would fall with the same acceleration. The second one, yes, people often think that the motion along the x-axis affects the motion along the y-axis and vice versa, but they're totally independent of each other. Okay, so the third common misconception. So people often think that collisions, or many collisions anyways, have sort of a winner and a loser. Nice collision loser, like that. um, and the winner of the collision, if it's like a big object colliding with a small object, or there's a lot of ways it could happen, but you think the winner applies a bigger force to the loser than vice versa. Well, really, um, anytime two objects are in contact, whether it's a collision or anything else, um, object one applies the same magnitude of force to object two, as two applies to one. And it doesn't matter what's going on in the contact, what the collision's like. Um, if you have a if a semi truck runs over a squirrel, the the squirrel applies the same force to the semi truck that the semi truck applies to the squirrel. Okay, that's yeah, you'd think so, but uh, the fact that there's a very clear winner and loser in that collision, right? And it's never the squirrel. Um, the forces are the same. What happens because of those forces is determined by unrelated things to the forces that are applied. Okay, the truck is a lot stronger than the squirrel. It has a lot more mass, and so I'm going to try to talk through that and help you sort of make sense out of that, because that's a bizarre concept to everybody. Like, so if a football team charges out of the tunnel at a game and they crash through the poster that says the team name and stuff, um, there's a clear winner in that collision. That, none of the football players get hurt and the paper gets shredded, but the paper applies the same amount of force to the football players as the football players do to the paper. Okay, so this is Newton's third law. And Newton's third law, if you translate it from Latin, I think it was written in Latin probably, it has wording something like this. Maybe you've heard this before. For every action, there's an equal and opposite reaction. Um, so that's the original wording. That's the wording that's known the best, but it's not very easy to apply that mathematically to problems. So we're not going to think of it that way. We're going to think of it in a more mathematical way. So for us, uh, Newton's third law, you can think of like this. For any two objects A and B that are in contact with each other, the force vector on body A by body B is equal to the negative force on body B by body A. And you can think of that so another way to think about this is if the force on A by B is this way with a magnitude R, then the force on B by A is the exact opposite direction and the same magnitude. Okay, so for example, and this is one that I think people often find confusing. This is one that doesn't really correspond to your intuition often, but okay, so this is supposed to be a baseball bat. Uh, okay. Free body diagram of the bat would have a force this way applied by the ball, and the free body diagram of the ball would have the exact opposite force R. So if you calculate that ball in order to, say it's hit 400 feet or whatever in the air, and you calculate that that ball to be hit that far would have to have a force applied to it through that contact of like, say, 4,000 newtons. I'm totally pulling that out of the air. That means that 4,000 newtons is also applied to the bat by the ball. That's true in any contact. Okay, so what does your intuition think about this? Well, I already said this is a common misconception, so this is one that a lot of people find sort of confusing. So what does your intuition say about this? There are some cases where this is pretty intuitive. You understand this pretty clearly. For some cases, it makes sense. So here's an example where you sort of know what's going to happen intuitively. So imagine that you're standing in the grass barefoot, okay, and a ball rolls over to you, and you look up, and some kids who were playing soccer, 10 feet or 20 feet away or whatever, ask you to kick the ball back to them. Okay, no problem. You kick the ball back, no problem. But now imagine the same thing happens. The ball rolls up to your feet, and you look up, and the kids are 50 yards away, and they ask you to kick the ball back, and you're barefoot, and you sort of think about it, and you're like, if I kick the ball back to those kids, it's going to hurt. And the reason it's going to hurt is, the difference between those two cases is to nudge a ball 20 feet, you don't have to apply very much force to it. To kick a ball 50 yards, you have to wind up and kick it as hard as you can. That you have to apply a big force to that ball to make it go 50 yards. And you know from experience that if you apply a big force to the ball with your foot, it's going to sting because the ball is going to apply that same force to your foot. Okay? So a case where it does make sense is you know that kicking a ball hard will hurt your foot. In other cases, but in some cases, it doesn't make a lot of sense to you intuitively, probably. Um, and I think a good example of that is this baseball and bat contact. Um, so, like a batter hits a home run. So, what's going on there? So, the batter swings, the bat makes contact with the ball. Um, the ball flies 400 feet before it lands. It's not a 50-50 thing where sometimes the ball keeps going the way it was going and the batter flies 400 feet, although that would make baseball more interesting, in my opinion. So, what's the deal? How is it possible that, what Newton's third law is saying is that the ball does apply the same force in an opposite direction to the bat? How do you make sense out of that? Well, the reason the ball flies and the batter looks like he isn't affected doesn't have to do with the contact force. It has to do with what happens to the object if you apply that kind of force to it. Um, so uh, when the batter hits the ball, and say there's a force of 4,000 newtons that the bat applies to the ball, and the ball also applies it in the opposite direction to the bat, 4,000 newtons. Okay, well, what happens so a ball, this ball is not touching anything else, it's in the air. It has a mass of 0.1 kilograms. So what happens if you take something that's a tenth of a kilogram, that's not holding on to anything, it's not in contact with anything else, and you apply a 4,000 Newton force to it? That's a very small mass. That force is basically, there's also a weight force on it, but the weight force is pretty small compared to that contact force. And so you're going to get something like, if you think of Newton's second law, you're going to have 4,000 newtons is equal to the mass of 0.1 times its acceleration. And so the acceleration of the ball is going to be 40,000 meters per second squared. Okay? And now think about what's going to happen to the bat. Okay? So your first thought is, well, the bat isn't that much heavier than the ball, a little bit. How much do you think a bat weighs? Do you think it weighs 2 pounds? Okay, so let's call it 1 kilogram. Okay, so it's 10 times as massive, but that's just the start of the advantages that the bat has. Okay, so it's 10 times as massive, but it's also being held by a person who weighs 200 pounds, and besides that, this person isn't floating in the air like the ball is. This person is wearing spiked shoes and is standing on the earth, and the earth is fairly massive, And so if you apply 4,000 newtons to this bat has the advantage of being more massive and being held by a giant thing, and that giant thing is attached to the ground in some way. And all of that just combines to the fact that 4,000 newtons applied to the bat just doesn't accelerate it very much, So it's not the matter that the bat applies a bigger force to the ball. It's all the other stuff going on that determines the winner and the loser. Okay, so when the truck runs over the squirrel, and we're talking about it a single instant, and that collision goes on for, well, parts of that collision probably go on for like a mile after. But think about like the first instant of contact or whatever. So there's some force of contact between them. That force of contact between them really isn't going to be that big, because how much force does it take for a squirrel's body to start to recoil? Not very much. And so the squirrel's going to, it was already dead from syphilis. Just to make the story less. So, but anyways, I should have said like a basketball or something. But anyways, it'll start to deform, and that'll lower the force. And so there'll be this small force that's applied to the ball, or to the tire of the truck. There's a downward force applied to the ball, an upward force applied to the truck. The truck can easily handle that force. It doesn't make any, it doesn't, there's no real noticeable effect. But if you apply that force to a squirrel or a basketball, there's a very noticeable effect to it. That's the idea. Uh, that is why it smushes. Yeah, otherwise it would mostly just, it would smush a little and it would just accelerate. If, like if it was in outer space, um, the truck would hit the squirrel and the squirrel would act sort of like a tennis ball. It would compress a little bit and then it would launch off. But because it tries to accelerate down, the Earth stops it, and it just, yeah, that's why it can't accelerate and it has to smush. Okay, so in some cases it doesn't make sense to us. Let me just write something about this baseball case. Um, so still, even though that seems confusing to most people when they first think about it, um, the ball does apply the same magnitude of force to the bat as vice versa. The bat accelerates less because A, it has more mass, and B, it's connected to a player that has way more mass. And C, uh, the player is anchored to the ground, which has way, way more mass. Okay. Um, when I first took physics in high school, I remember my physics teacher giving this one example, and I mention it every semester because I think it sort of clarifies what this means, and it's also funny, which is a good combination. So when I took physics, there was like a hot new up and coming boxing prospect in the heavyweight division named Mike Tyson. He he had not yet won the world championship, but it was pretty clear he was going to, and he just destroyed everyone. Everyone was like afraid to fight him. Um, and my physics teacher was like an older, out of shape guy, and he's like when we talking about Newton's third law, he said, I wish they'd give me the Nevada Boxing Commission would give me a chance to fight Mike Tyson. I guarantee that I could hit him as hard as he hits me. And he drew this picture. So that's Mike Tyson's arm. And this is his face. And the part that's funny about it is Newton's third law literally and like unambiguously. I'm not, it's not a misinterpretation. It says that if Mike Tyson punches a physics teacher's face with 2,000 newtons of force, the physics teacher's face hits the glove with 2,000 newtons of force. And uh, it's, I mean, that's why boxers get broken hands a lot, you know? Uh, but the funny part is because it's not a very effective boxing strategy to attack a boxing glove with your face, you know? Um, Body diagram of face. I'm going to skip all the, you know, there's stuff, the connection at the neck and all that. But that's not what we're worried about. Um, there's a force over here of, uh, you know, I don't know, let's say 5,000 newtons. And that means that a free body diagram of the glove, there's a force of 5,000 newtons going this way. And if um, if people had their brains inside their hands, then that is how you would box. You would attack people's hands with your face. Well, yes, because remember the way what you do when you draw a free body diagram is you draw a closed outline of the body, and then you apply the weight force, and then you go around the boundary, thinking about what forces are applied. So, what forces are applied, like what things are in contact with the face around the boundary? The glove is, and the force that the face applies to the glove doesn't show up in that free body diagram. Um, yes. Well, I suppose, I mean, there's sort of the issue of how it's distributed. If you like if you used a sharp knife, I imagine you could cut through a bone with less force than that. You know what I mean? And so it's sort of a matter of how much it's spread out. Uh, but yeah, I don't know. I just pulled that, so that might be totally wrong. I think I came up with that number from thinking about how strong uh, Ivan Drago's punch was in Rocky Four. So that's not a very careful way to determine that amount. Um, okay, so I'm going to do an example. Yes. Yeah. Yep. Yeah, that's right. Well, so yeah, the difference between the speed of the bat and the speed of the ball coming in determines how much the ball compresses, and then it's that compression force, you know, that it becoming uncompressed as well as the speed of the bat that determines where it goes. So that's the relationship between those, I guess. Right. Yeah. If it was a Play-Doh baseball, you know, something that didn't bounce at all, I don't think the speed of the ball coming in would have any effect on how far it went. Only the speed of the bat would matter. Okay, so let's do an example. All right, so let's say that there are three carts rolling along a horizontal surface. 1 kilogram, 2 kilograms, and 3 kilograms. And then there's forces applied to the outside carts. A 20 Newton force going this way and a 10 Newton force going this way. And let's say that what we want to figure out is what's the force vector on the 2 kilogram cart by the 1 kilogram cart. The first step, no matter how you do this, who remembers what the first step is in a problem like this? What do you want to isolate first? What? That's right, do a single. So we're going to do a free body diagram. The thing we're going to isolate is the whole system, all three of them. And the reason for that is we can use that to calculate the acceleration. And you'd see if you isolated any of those individual ones, we couldn't calculate the acceleration without going on and doing another step. So first, we're going to isolate the three carts together. And calculate the acceleration vector. Second, in this case, so what would you think? Like your natural inclination would probably be we're going to isolate the 2 kilogram cart next because we're trying to calculate a force on that. The problem is that there are two unknown contact forces on the 2 kilogram cart, one on each side. And so you wouldn't be able to solve it that way by itself. And so there are kind of two ways to do this problem. And the first is to, so the problem is that this isn't at the end of the string in either direction. So you want to isolate the entire string from one of the ends, including the piece that you want. So we're going to isolate the 2 kilogram and the 3 kilogram part as a single unit. Then the only unknown we have is the force, the one's applying to 2, and we can solve for it. The only horizontal unknown. What? We don't care about a 3 because just we weren't asked for it. Oh, so why don't, okay, so we'll see when we draw the free body diagram why, but I guess the short answer is for the contact forces, you just go around the boundary looking for contact. And if you isolate both of these together, that boundary between those two is not the boundary of your isolated system. All we care about is the boundary of our isolated system. Yeah. If you don't know the acceleration yet. If you, yeah, so like a case where you're given it is like if you have objects stacked on top of each other in an elevator, then you already know what their acceleration is because you're given the acceleration of the elevator. And then you can skip that step. And now that we've talked about Newton's third law, there's a third possibility. So now we're going to pretend we didn't do part B. And now we're going to isolate the 1 kilogram part. We're going to use that to calculate the force on 1 by 2. And if we know the force on 1 by 2, then Newton's third law says the force on 2 by 1 is the same magnitude, just in the opposite direction. Yeah. So for step C, we're going to isolate the 1 kilogram cart. we're going to be able to calculate the force on the 1 by the 2. And what Newton's third law says is that if you know the force on the 1 by the 2, the force on the 2 by the 1, that same contact force just acting on the opposite body, has the same magnitude in the opposite direction. So, okay, so let's go through this. Just the opposite direction. So it'll be opposite vector components if you do it as components, and it'll be just an arrow in the opposite direction if you're thinking of it that way. Okay, so for part A, a free body diagram of all 3 carts together. There's the weight down. That's the mass of all 3 together times 9.81. So that's 6 kilograms times 9.81 is 58.86. And now we go around the boundary. There's a pushing contact from the ground. I'll call that N total. And now go around the boundary. If you think of there being a boundary between the 2 and the 3 and the 1 and the 2, those aren't boundaries when we're isolating them all together, so we don't have to worry about those contact forces. So now we just have to worry about the 10 Newton force applied this way and the 20 Newton force applied this way. And now we can go to Newton's second law. Oh, I didn't say anything about the coordinate system, but for rolling and sliding problems, we always have the y-axis pointing right out of the surface. So in a case like this, it's just the usual coordinate system with the y-axis up and the x-axis this way. Rolling and sliding problems, we always choose a coordinate system with the y-axis pointing straight out of the surface. That's how we get those rotated coordinate systems with inclines. In this case, the surface is the ground, so straight out of it is just up. And then we have the coordinate system that we're most used to. Well, the system is rolling, so you use that same coordinate system. Well, we always had the y-axis pointing straight out of the surface. I might have not mentioned that it satisfied that requirement, but if you look back, it did. I just forgot to say anything about it. Newton's second law, then. Well, it's not always equal to the weight, but if you solve for it, you'll see that it is in this case, yeah. No, because the weight is not the force that the cart applies to the ground, except under certain conditions. It's the force gravity applies to the object. So Newton's second law, the 20 Newton force is in the positive x direction. So you have 20, 0. The weight force is in the negative y, so 0, negative 58.86. Normal is in the positive y, so 0 N total. The 10 Newton force is in the negative x. And for rolling and sliding problems, the acceleration is always a0, so this is equal to 6 times a0. What are we trying to calculate? That's the mass of what we're isolating here, 1 plus 2 plus 3. Yeah, we want the acceleration, and this is the acceleration vector. We just need to figure out what that variable a is to finish this, And so all I need to use is the x equation. So the x equation from Newton's second law says 20 plus 0 plus 0 minus 10 is equal to 6a. And so you get 10 is equal to 6a, or a is equal to 1.6 repeating meters per second squared. And now we take this positive 1.6 repeating, plug it in to the acceleration vector, and we get that the acceleration of this system is 1.6 repeating for x, 0 for y, or in other words, that's in the positive x direction, so you can think of it as an acceleration that direction with a magnitude of 1.6 repeating meters per second squared. Okay, so now we're going on to the second step. Anybody have any more questions about that step? All right, so part B, we're going to isolate the 2 and 3 kilogram parts together. Okay, so the force is acting. There's a weight force acting down. This time our system has a mass of 5 kilograms. So the weight is 5 times 9.81, 49.05. There's a pushing contact up on the wheels. That's not the same normal as it was before, because this is only on 2 of the wheels of 2 of these carts. I'm going to call this N23. Then there's a 10 Newton force this way. And then we don't have the 20 Newton force because that's being applied to the 1. So that's over here somewhere. That doesn't touch this boundary. So the only other contact that this boundary makes with the outside world is the contact that this makes with the 1 kilogram part. Well, it depends on the masses and stuff. In this case, it's going to be around 20, but if that hadn't been a 1 kilogram cart, it had been a 200 kilogram cart, then it would be very far from the force that was applied on the side. So over here, we have this unknown contact force R. Any questions about that setup? Okay, so Newton's second law says, so this force R is in the positive x direction. R0 plus 0, negative 49.05, plus 0 into 3, plus negative 10, 0, is equal to the mass of the system, 5, times the acceleration of the system that we just figured out in part A, so 1.6 repeating 0. What are we trying to calculate? Yeah, we want R because we're trying to fill in this vector. This is the force vector on the 2 by the 1. We just don't know what R is yet to finish it. And so again, all we need is the x component, the x equation. So the x equation says r plus 0 minus 10 is equal to 5 times 1.6 repeating, which is 8.3 repeating. And so R is equal to 18.3 repeating. Now we can plug this value for R into the force vector onto by 1, and we get that the force onto by 1 is equal to 18.3 repeating 0. What direction would that arrow be? Yep. So that way with a magnitude of 18.3 repeating. Yes. Yep. Because, I mean, we're just talking about what the contact force is here at that boundary, no matter what's going on. Yep, negative 18.3 repeating 0, or 18.3 repeating with the arrow in the opposite direction. Yes. No, that would be fine. If you could just say the opposite of that. I mean, what this problem asks for is the force on 2 by 1. So this is actually what we're looking for in this problem. But so now that we're done with this approach, I'm going to pretend we didn't have this result, and I'm going to use a different approach to get this. We're going to get the same answer, but we're going to do it by isolating the 1 kilogram part and using Newton's third law. Okay. And it's cool how it works, I think, because if you look at what the free body diagram looks like here, there's a 20 Newton force that doesn't appear in our free body diagram or in our calculations. It obviously has something to do with the motion. When we isolate the 1 kilogram part, we'll have the 20 on it, but we won't have the 10. It feels like there's this information that they're not sharing with each other, and yet we're going to get the same answer in both cases. And that's the answer to history, yeah, is that in part A, which we're using in both of these two approaches, we calculated an acceleration using both the 10 and the 20. And so that's how that information sort of sneaks in, even though it's not explicitly there. Okay. So part C. So now we're going to do a free body diagram of the 1 kilogram cart. There's a weight force down that's equal to the mass of our system, 1 kilogram times 9.81. So that's just 9.81 in this case. There's a upward pushing force from the ground. I'll call that N1. Over on the right side, this is in contact with the 2 kilogram cart. And that's a pushing contact, so it has to be toward the chosen body. That's R. Remember, we're pretending we didn't do part B. Otherwise, we would automatically be able to fill all this stuff in. But and then over on the other side, there's the 20 Newton force. Any questions about the free body diagram? Okay, so Newton's second law says 20, 0 plus 0, negative 9.81 plus 0 and 1 plus negative r 0 is equal to the mass times the acceleration, 1.6 repeating 0. What we're trying to find is this vector. This is the force on the 1 by the 2. And to do that, we just have to solve for that variable r. So the x equation from Newton's second law says 20 plus 0 plus 0 minus r is equal to 8.3 repeating, no, think of my old math, is equal to 1.6 repeating. So r is equal to 20 minus 1.6 repeating. So r is equal to 18.3 repeating. Nope. So the variable r is positive, but now we have to substitute that into the vector. Okay. So the force on the 1 by the 2, when you substitute this into the vector in the dotted red line, is, here's where the negative comes in, negative 18.3 repeating 0. Or if I was going to write that as a magnitude and an arrow, what direction does that point? To the left. And now that we know the force on 1 by 2, Newton's third law says the force on 2 by 1, there's sort of two ways you can think about this. First, you can just switch the signs of all the components. So that's 18.3 repeating, negative 0. That's still 0. Or you can keep the magnitude the same and switch the direction of the arrow. So that's two different approaches. Same answer. Any questions about that? Okay. Test on Tuesday.